And I also wanted to thank Professor Korgel for the invitation. Really happy to be giving this presentation today. Um, and I guess I'll start off by just giving a little bit of background about myself, and then I'll just kind of launch into it. So I do have a technical background. Well, first of all, I'm the founder and CEO of UbiQD, and I'll be representing them today in this presentation and telling you about what we're doing at the company. But I have a technical background, even though these days I'm spending my time doing more business-related activities. I have a PhD in material science from University of Illinois, and then before that, I was studying electrical engineering and physics at University of California, Santa Barbara. And then after my PhD, I had a fortunate opportunity to come to Los Alamos National Laboratory to continue my work on nanomaterials, specifically quantum dots, in the chemistry division with Viktor Klimov at Los Alamos National Laboratory. And it was there that really was able to sort of drill down on this set of materials and develop a kind of passion for working on industry related problems because we were collaborating with Sharp Corporation under a corporate research and development agreement. And unfortunately, Sharp kind of fell on hard times, and so we had developed this technology, but they weren't really going to carry it forward, and I saw that as an opportunity to start the company. And so about 4.5 years ago, 2014, I spun out effectively. Like we call it spinning out, but there's not really any spinning, and it's really not like you're coming out or anything. You're just sort of like out there, like you jump off a cliff and you're trying to figure out how to fly before you hit the ground. Is what it's like. But so I spun off the cliff, trying to figure out how to fly back in 2014, and it took me about 1.5 years or so to really start developing a team and figure out what we were doing. And I can talk more about that maybe on another panel. But today I wanted to focus on really one of the most exciting aspects of our technology, or use cases anyway, in clean energy, and specifically in solar, and using our quantum dots to generate electricity from windows. And I want to acknowledge, in addition to Los Alamos National Laboratory for helping, where I helped develop this technology, and we're licensing IP from there. I want to acknowledge National Science Foundation. We received a Phase 1 SBIR from them in 2016 that enabled us to sort of do the proof of concept work around putting quantum dots into glass to generate electricity in windows. And then we were successful in that first phase, and got a Phase 2, which started last year, I guess about the middle of last year, which is enabling us to work for another 2 years to carry it further. And the vast majority of the work that you're going to see in this presentation was funded by National Science Foundation. And I guess I should also note that we have an intern working with us right now from UT Austin, Dan Hook. What I'm saying, Dan's in the room right now, so you could say hi to everyone.
Hi, Dan.
And Dan is also funded by National Science Foundation I believe under a slightly different program, but to be eligible, I believe we had to have this grant that we have at the company. So just want to give a big shout out to National Science Foundation and thank them for all of their support. So, this is going to feel a little bit like a pitch, I guess. I spend most of my days talking to investors and potential partners, and that's basically, you get a short opportunity to present the concept, why they should invest, why they should partner, and then hopefully that'll lead to a second conversation. And there's a sort of a structure for that kind of presentation that I figured out over time. So it might feel a little bit different than the typical technical talk that you guys are used to seeing, and maybe a little bit more businessy. So we'll just see how it goes. But the way that always needs to start is with the problem. In this case, there are kind of two layers of problem. There's the bigger problem, which is driving the smaller problem, or sort of what I'm calling the big problem driving a market problem that we can address with our product and our technology. And this is kind of preaching to the choir. I know that you guys at the Center for Next Generation of Photovoltaics already appreciate the big problem, but I just thought I'd throw it up there. It's essentially that CO2 is at alarming levels that we haven't seen in our atmosphere for, I believe, more than 6,500 years, as far back as we can go, essentially. CO2 has never been this high, and it correlates strongly with the rise in temperature, global temperature. And that has to do with CO2 being a greenhouse gas. And CO2 is something that's generated by the burning of fossil fuels. And so ultimately the problem is around reducing our production of CO2 or the release of CO2 in the atmosphere. That's driving climate change, which will have all sorts of impacts, that most of which are not good. The actual market problem that's caused by this is that, of course, we want to generate our power with carbon-free sources of energy like photovoltaics, and photovoltaics are a good one, not the only solution, but a good one. And I'm not going to go into all the arguments for photovoltaics because I'm sure that you guys would agree with me on that. But it's really in those urban centers where the space available for renewable energy for photovoltaics is the least, but the demand for electricity is the highest. And just take this picture of Austin that I pulled from the internet. That you look around in this picture on the Austin skyline, you won't see any solar cells really. You might expect to see them on some of those rooftops, but there's not really space to put them. Even if you put them on rooftops, a lot of these roofs are not flat. They might be used often in urban centers are used as leisure spaces, like places to hold cocktail parties or the HVAC systems. There's just not space in a city to put solar cells, but that's where the demand of electricity is the highest. And there's global urbanization that's been going on for decades, even centuries, that's driving more and more people into cities. And this is a really interesting chart showing, the different, countries and how the population has migrated into what they're calling an urban area. And like, for example, in the United States, 82% of the population lives near an urban area. In Japan, it's even higher. And you can see all of these are sort of trending up and to the right. And you have some countries that are, they're growing the fastest, like China, where it's even a steeper trajectory. But the point I'm trying to make is that globally, people are moving into cities. And then it's in those cities where electricity prices are the highest because the demand is high and the electricity supply is more limited because there's not any local generation. People aren't putting power plants in cities because they're ugly and there's not space. That's not a good use of the real estate. So, for example, in New York, the price of electricity is almost double on average what it is in the United States. And if we want to put solar, renewable energy into cities, the one thing is certain is that the aesthetics are not. No one's going to compromise on the aesthetic. We're not willing to put an ugly power station in a city. We're not willing to, make an ugly-looking building just to solve this problem. As much as we'd like to think that that would be a good compromise, it just simply isn't going to happen. And you might think, well, that might be true in like a fancy place like New York, but what about in a more of a developing country? For example, in Thailand, this is one of my favorite buildings in the world. It just completed about a year ago, called the Maha Nakhon Tower. There in the middle, looks almost like a pixelated, like a tower out of like a Nintendo game or something. And there's some really cool pictures online if you look around. But basically, this is like an all glass skyscraper with really beautiful design work. And there's nowhere you can put a solar cell, partially because the facade of the building needs to be transparent because people are living and working in that building. And they want to be able to utilize natural light and see outside. But it's also, the architect's vision to have this beautiful structure, and he's not going to compromise, to be able to improve the energy efficiency of the building. So, but it's okay because we've got the solution with quantum dot-tinted glass. And I'll explain how that works in a second, but it's a simple, essentially seamless way to integrate electricity production directly into the facade of the building while maintaining transparency. And here's how the concept works. We put our materials into glass. It's not actually in the silicon dioxide. We can do a coating on a sheet of glass, but more commonly, we make a laminate structure where our material is in a polymer in between two sheets of glass. There's different approaches to making a luminescent solar concentrator, which is what this is called, but we do it as a laminated sheet of glass with quantum dots in the inner layer. But anyway, the quantum dots absorb sunlight partially, and then they are glowing. That's what quantum dots do. They're very effective at absorbing and then re-emitting that energy as luminescence. That luminescence, about 70% of it gets trapped in the glass by total internal reflection. and then the light has nowhere else to go but towards the edges where it can couple out. And so I'll show a picture on the next slide or two that shows the effect a little bit better, but you can put solar cells right there on the edge to capture that light and generate electricity. So a simple idea: tint a window with quantum dots, capture the light that they emit at the edges, put solar cells there, and save the world. So this is kind of showing what it looks like. I like to show a demo whenever I give a talk, but this is a kind of it's not so possible to show the demo. So here's a picture of what a demo might look like. This is a sheet of some of our glass with some red quantum dots in the sun, and you can see that edge effect, the bright orange/red glow that's being guided to the edges, and it's called a luminescent solar concentrator. For those of you who don't know what a quantum dot is, I thought I'd just dedicate a slide or two to that. These are really tiny particles of semiconductor that are effective at manipulating color and light. In other words, they're photoluminescent. They can absorb one color and then convert that to a new color. And why are they called quantum dots is because of a quantum effect of having a band gap that's changed with the size of the particles. So we can make this rainbow of colors like you see in these vials with the exact same compound. This happens to be copper indium sulfide. But just by changing the size of the particle, we change the band gap, and so we change the color of light that they absorb and emit. And this concept isn't new. It's been around for about 35 years or so. But what we've developed was a safer, much lower cost, and more stable version. And it turns out there's one more really important property for this application, which is that they have a large intrinsic Stokes shift, which means they don't absorb their own luminescence very strongly. So that enables you to guide the luminescence through the material over, say, a sheet of glass over a square meter. Just a little bit more specifically on our quantum dots, they're also exciting because we're able to access a wide range of colors, not just the visible, but deep into the near IR, which is pretty useful for this application because we want to make kind of color neutral window tint and dial in the luminescence to hit the band edge of silicon or perhaps other kinds of solar cells, but we mostly use silicon. We can also make materials with really high quantum yield. That means for every photon that gets absorbed, up to nearly 100% of those get converted into a photon emitted. And that's true not just for the visible, but also the near IR. And then we have a scalable, low-cost manufacturing approach. Most of what we're doing with windows is with copper indium sulfide, but we can also make alloys, and that enables us to go beyond deeper into the near IR. And if you do want to play around with these materials, they're available on Strim. We distribute to them for the research market. I'm not going to go into the details of our manufacturing process, but I'll show a few pictures of what it looks like. It's a liquid phase reaction for the core and the shell. We have a shell that protects the core from the outside world, and that's typically zinc sulfide. But people kind of make fun of quantum dot chemists. Sometimes they call it bucket chemistry. Compared to like organic chemistry, some chemists might argue that it's a little bit simpler. But I do like to make this point to investors that it's not overly complicated, where we just essentially add our materials, precursors, solvents, ligands, we heat it up, we wait for some period of time, and then we cool it down. And this is a scalable approach. We call it the heat up method, as opposed to a hot injection method where you have to mix precursors together at high temperature to have a short nucleation event. So we think we've got a more scalable process because of that. After that, you have to sort of purify out the good stuff from leftover precursors and ligands and solvents and such. And then we put that into a polymer resin, and then that comes out the other side as a film, which then can go between sheets of glass to make a window. Attaching the solar cells at the edge is something that we spent a bit of time optimizing and working on. I'm not going to spend too much time on it other than to just show this picture that you can get small solar cells and adhere them to the edge in the right way and then solder them up and make basically it's a module at that point. So we're frequently seeing 30, 50 volt type voltages coming out of even a small window. But you can optimize that because you could connect some of them in series or some of them in parallel to achieve whatever combination that you needed. So the value proposition is pretty straightforward. It's developing a drop-in solution, In other words, we want to have our material go into existing manufacturing process for windows. And the way laminated glass windows are made today, there's extruded polymer. Extruded means it's melted and then comes out the other end and pulled into a sheet. And so we want our materials to go directly into that extruded polymer interlayer. And then once that's done, it can essentially go into the same manufacturing process for laminated glass, which means it goes to a laminator who sources glass. They do like an autoclave type of process to adhere it all together, and then it can be manufactured into what's called an IGU, insulated glass unit, and so on. And then at some point along the way, the solar cells would be added along the edge and wired up, and there you go. So we don't want to disrupt the value chain. We want to leverage it. And what goes along with that is that we don't have any lines in the glass or other aesthetic. I mean, obviously, this window that I'm showing in this picture is orange, and you might think that was a negative because no one wants an orange window. But we can make different colors, including color neutral. But other approaches to making solar windows are compromised on the aesthetic because they generally have to pipe out the electricity from the glass, and that means they need transparent conductors and patterns, which leads to lines and other distortions. And because it's so simple and low cost, and the model that, and I'll show some data on this, it's a pretty fast payback time. So if you're the customer and you're thinking about whether or not you want to do this, it's a pretty smart investment, mainly because after those 5 years, you've paid for the product, and then you get return on that investment. And so if it lasts 20 years, it's a pretty good rate of return, actually. And compared to typical photovoltaic systems, like for example on a rooftop, you might see 7-year payback time. In the desert, like in a solar farm, maybe you can achieve 4 years. So we're kind of in the range of typical payback times, and and that's why solar is blowing up. That's why the industry is growing so fast, is because the cost has come down to a point where it's a reasonable investment for the user, and that's still the case with our technology. You're not going to compromise that to have it be transparent. So there are a lot of opportunities to deploy this technology, not just with the obvious ones. And actually, our first market is in agriculture and greenhouses. I'm not going to spend too much time talking about that today, but the takeaway: 54 billion square feet of global footprint for greenhouses. That's a ton of greenhouses, and it's growing almost 10% a year. So that alone is a pretty large opportunity. And obviously, greenhouses are mostly transparent. Electricity is the biggest expense for a greenhouse operator, typically. And then commercial buildings is the one most people think about, like skyscrapers. That's about $100 billion a year, at least total sales of glass for commercial buildings. And then automotive is another one that's interesting. It's kind of a difficult market to attack, but there's a lot of glass going into automotive. Just take a look at the Tesla Model 3, which has about a 2 square meter, a little less than 2 square meter sunroof. And the value proposition for automotive is better miles per gallon, alleviation of range anxiety, and you can do really cool things if the car is powered when it's off. So here's just a chart, not hard to find these, showing the anticipated growth of building integrated photovoltaics. It's a multi-billion-dollar industry today and expected to grow to tens of billions over the next 10 years or so. Mostly it's rooftop right now, but as buildings get taller and you go into urban areas, there's nowhere else to go but down the sides of the building, down the facades, and that requires transparency. So I'll use the next, 20 minutes or so to talk about where we're at with this technology. I mean, I think I've probably convinced you that the concept is there. It's cool. It sounds like it could work. So does it work? And where are they really at? So we've actually made a ton of progress. And one of the things I like to highlight is that we're making insulated glass units now for the first time. These are double pane windows with a typical spacer, working with a company in Albuquerque called GlazeTech. And that picture on the left is them actually fabricating one of the first IGUs that we made. And on the right, that's a picture of it with a typical New Mexico scene in the background. Spent a lot of time also working on trying to optimize the edge. There's different ways you can attach solar cells, different configurations and soldering them up, different kinds. You could use gallium arsenide, you could use silicon, you could use SIGS solar cells, and they all have different trade-offs in terms of cost and performance, and we're still working on that, but we've come a long way. You also have to figure in the effect of the IGU, which needs to be sealed, and that can affect the optical properties and coupling of light through the glass. Another key one is the quality of the glass. There is a trend in the industry moving away from typical float glass, which has this green color. And if you take a sheet of that and look on the end of it, it'll look almost black. And that's because light doesn't, as they add iron into that glass, which is part of the manufacturing process, iron will absorb, forms iron oxide essentially, and that will absorb light, which you wouldn't notice through like an 1/8 inch or a 1/4 inch. But when you look the other direction, it makes a big difference. And we actually have to couple light through the long direction. So that glass doesn't work very well. I'm not even showing the data here, but we have a paper that you could look at that has the lowest quality. Here I'm comparing acrylic, which is a common waveguide that people use for luminescent solar concentrators, with low iron float glass and with 0 iron float glass. On the left, you can see some absorption spectra, which is estimating the optical density through a full meter of the glass. And polymers are not that great, especially as you go into the near AR. They have some overtones that absorb, CH vibration overtones that absorb strongly there. And then as you go towards better quality glass, iron itself has an absorption band in the IR. But as you get to higher quality and essentially remove the iron, that goes away. And you can think of like quartz or optical quality glass that you might use for cuvettes. And anyway, on the bottom right, sort of the summary of, and I'm sorry, there's kind of several different effects being convoluted there, but the summary of how those perform. And long story short, the lowest iron or 0 iron performs best, much better than acrylic and better than low iron. And these numbers for like our EQE and IQE, those actually aren't published, so you guys are seeing these for the first time. And by a wide margin, these are the highest numbers that have ever been reported. I believe the highest EQE ever reported, separate from us, was around, I don't know, 5% or so. And that's photons being converted into photons on the edge. Photons being absorbed, converted to, photons incident being converted to photons emitted on the edge. If you divide by the absorption spectrum, you get the IQE, and this is telling you how close to your potential are you. And we're approaching 50% for the best case. So essentially half of all the photons absorbed are being re-emitted at the edge. And the intrinsic limit for this material, or if you don't do any tricks with total internal reflection, is around 70%. That's just because there's an escape cone of light that can get out if it's emitted in the randomly too close to normal incidence. And then that translates into, for the best case, our current record certified was around 3%. And then if you add a mirror, which sort of simulates having a low E coating, around 3.6%, which is not published yet, but is the record efficiency for a solar window to the best of our knowledge. And here's some pictures of the Nrel certification. As I mentioned, it behaves a lot like a module with about 20 volts in this case, VOC, and then what's that, around almost 60 milliamps per, and this is over about 6-inch by 6-inch device. So that would translate into roughly around 3.4 watts, I believe, per square foot, which is pretty good. We think that the target needs to be, or at least the milestone to commercialize, is around 50 watts a square meter, or around 5 watts a square foot, and we're almost there. Just to give you a sense of how far, our progress, this time last year, our record was standing at about 2.9% with the mirror, and I think around 2.3 or 2.4% for without the mirror. So we're making progress, and we hold the record. So as far as reliability, that's something that a lot of people wonder about. Will this stand up to 20 years, 30 years of sunlight? And we're a 4-year-old company, so it's very challenging to convince someone that the answer is yes. But when we put the material between sheets of glass, that's essentially the best kind of encapsulation you can have to keep the dots protected from the outside environment. The main degradation mechanism is photooxidation. So if we can eliminate oxygen ingress, then the material seems to survive for essentially indefinitely. Here's some data just backing that up. On the bottom right, we've got 3,000 hour study. I think this is about at 1x sunlight. And on the left, it's accelerated by another, I think it's 3x or so. And then these are running constantly, whereas the sun is rising and falling every day. So equivalent of about 10 years of reliability in the sun. Of course, we're working to push that further and really understand how we can accelerate if we are effectively accelerating degradation. And it's challenging for various reasons. The least of which is that the actual real world is one sun. So if you crank up the intensity and it's at ambient temperature, if you crank up the temperature or crank up the intensity, you can introduce nonlinear effects that can be not representative of what will actually happen. And then sometimes, like on this bottom left one, when you crank it up too much, other things might fail in your tests, like these LEDs. These very high power LEDs actually broke first before the sample did, which is kind of encouraging, I guess. Okay, so it's not just about does it work and is it stable, it's also can you make it big enough to actually make a product. And we're working on that. Our milestone that we're aiming for is a square meter by the end of March. And we've actually prototyped without dots with some dye by our manufacturing process, actually at a square meter. But with the dots, we've made up to about 5 square feet. There's an example on the left with some visible dots, but we also done it with some near IR dots like you see on the right. And so they do look a little bit brown with the near IR, but there are ways of balancing that out. But the near IR is what would be used, we expect, in commercial buildings. We've worked with Nrel to try to essentially model what the performance would be expected to be in real world situations, because the sun is moving over a building. So for example, in the morning, the east would be getting more sunlight and the west could be getting less. And then maybe in the winter, you expect more from the just the south facing side. So how does that all average out over a year? And here's just some examples of that for Miami and Tokyo, taking into account actually the weather patterns for those places, because Miami sees a lot more sun than Tokyo does, but Tokyo might have more diffuse light, which enable maybe more uniform production. And so I'm not going to go into the weeds on all this, but we've got modeling for I believe almost 30 cities now with actual weather data. And it comes out to several gigawatt hours for a typical skyscraper, which is not enough to power the building, but correct me if I'm wrong, Matt, but I believe that's on the order of around 10 to 20% of their needs. So we're not necessarily talking about a net zero building, but that's okay because it does have a reasonable payback time, and you shouldn't necessarily judge it whether or not it can power entirely the building. You're always going to need to power the building at night, for example, when the sun's not shining. But if you can improve the energy utilization of the building simultaneously with adding production, you can approach net zero. So when I say 10 to 20%, that's a typical building, not like optimized for their energy use. We're moving in the direction of net zero, but not there yet. And then this is just giving some examples of how things vary by season for Miami. You can see that in winter there, as I was saying earlier, the south gives you the best production, but east and west look pretty good. And then when you go to, so that's the top left plot. If you go to summer, like below that in July, the east and west are performing better. And then also in the spring, east and west perform better. And then things get kind of averaged out in the fall. As you can imagine, this would vary by location, right? If you're close to the equator, it could look a lot different than if you're, like, say, up in Canada or something. And then, like I mentioned, it does take into account weather patterns. So you can go back and look at a specific day, like October 1st in, I don't know if the year 2009, Miami, guess what? It was a cloudy day. So all 4 sides of the building were seeing the same production muted, as opposed to 4 days later on October 5th, where you had a bright sunny day and you get that more typical production. But not just production to get at the value proposition, you also have to understand the cost. And this is something that a lot of scientists, no offense to the scientists on the call, are a bit naive about. There's a lot more that goes into the cost besides just your part of it. And even, so the dots are just one part of the materials. Then you also have to add the delta for the higher quality glass. For low iron, it's about, as I was told a couple days ago by industry leader, about 38 cents a square meter to go to low iron. And then laminated glass can be a little bit more expensive, and things like that have to be considered. And then you have to add the solar cells. So we have our estimated added cost, but then that gets compounded as well. You have to take into account that the material changes hands in the value chain and gets marked up. And so we think about all those sort of things, but then that's only about half of the total cost, because you have the balance of systems, which includes like the labor, the sales tax, the contingency, the shipping, the wires, the inverters, permitting, all these other costs that maybe you could, if you're not careful, forget about, end up being a huge portion of it. You factor that all in to get to your final, installed cost. And Nrel knows a lot about this, so they helped us model how would this project be financed. Here's an example of one, about 40 to 50 story building, which would produce it's about a 1.3 megawatt system. And that would cost the purchaser about $1.8 million. But then they would have, including all those additional costs, but then they have a tax credit, 30% ITC tax credit, at least that's currently in place, of 30%. So that drops it down to 1.2 million. And then there's some statutes that give you accelerated depreciation, which is a favorable treatment by the IRS, which effectively acts like cash flow in the first 5 years, because that's it's creditable against your taxes, and so it essentially is cash. And that gets you to your 4.5 year payback time. You can see where that line crosses over zero, and then gets you to an internal rate of return that approaches 20%. That's a pretty good investment to make for a hard asset that over the long haul returns 20%. Just to summarize on solar windows, where we're at, and why we think it's the future. We have excellent aesthetics. There's no lines or distortion, great color options. It's a simple approach, scalable approach, low cost approach. We have great long-term stability. Try to imagine organic material surviving for 20 to 30 years. And actually, that's several companies that are pursuing organic photovoltaics for solar windows. It's just hard for me to imagine them surviving that long, because they are so susceptible to photo degradation and moisture and whatnot. We do have the highest performance. We're transparent about it. We've had it third-party certified and published, and we intend to publish the latest result as well that I just showed earlier. So I want to take a few minutes now to just talk about one other opportunity with greenhouses. I mentioned that was one of the markets for solar windows, but we've seen that as we talked to greenhouse operators and we proposed this idea to them, overwhelmingly they were pushing back on, well, how's this going to affect my crop yield? Because that's more important to me than anything. I'd love to reduce my overhead costs, i.e. my electricity bill, but if that's going to compromise my production, it's a no-go, because it's already difficult enough for them to stay afloat and be profitable as a farmer. And so they're not willing to compromise yield. So we started thinking about, well, maybe there's some color that we could use that would not hurt the yield and we could still generate electricity. And then we kind of had this aha moment that, well, maybe we just forget about electricity for the first version of this product and just make a color that's going to boost yield. Because crops, photosynthesis is driven by chlorophyll that has a certain absorption spectrum. And maybe we can just dial into that absorption spectrum. So long story short, we've done a number of studies now over almost 2 years. And this is summarizing some of those latest results in-house. These aren't pilots, so this isn't necessarily going to be what you'll see in a commercial setting. But in-house, we've seen up to 49% yield improvement for tomatoes, faster early stage growth. With cucumbers, we just completed a trial that was showing up to 54% increase by weight, also faster germination. And that is a big opportunity, like I mentioned, 54 billion square feet of global greenhouses. So we also like that it's a simpler product. We don't have to muck around with the wires and the solar cells, and we're already making film right now. So maybe that's the minimum viable product. So we launched that under the UbiQD brand about 3 months ago, and installed in 8 commercial greenhouses now. Just real quick how it works, we essentially shift the spectrum of sunlight by mostly capturing blue and green photons and moving them to wherever the peak emission is. And for what we're focusing on with this first product, like you saw on the last slide, it's orange, kind of around 600 nanometers, which seems to work well. There are various target segments, strawberries, cucumbers, tomatoes that look interesting. There's one other crop that's kind of interesting. I don't know if anyone has any ideas about what that crop could be. But we're thinking that maybe southern Colorado is a place where that crop, where we could find some customers with that growing that crop. But it's still somewhat tentative and it is exploratory, I guess. But NASA took notice of this work that we've been doing on agriculture as well, and through the SBIR program, or STTR, I guess. We partnered with University of Arizona to explore using this for long-duration space missions. And so we won a kind of preliminary proof of concept grant with NASA. And there we're looking at lettuce. I'm not ready to share any of the results, but they look quite promising. A couple pictures here. We're comparing an orange-colored film and a red-colored film, and this work is happening at University of Arizona. So look for some results from this study, maybe mid-year, out of University of Arizona. We do see big opportunities in agriculture, in addition to the windows. Just to highlight a few of those, there's this first one that I mentioned that's growing fast in North America in particular. I've kind of mentioned the size of the greenhouse market several times. It's kind of mind-boggling how much vegetable production happens globally. 177 megatons of tomatoes, 81 of cucumbers. It's multi-hundreds of billion-dollar industries. So if you can boost that production with a simple, low-cost product with a fast payback time, less than 6 months, looks like, then it could be a game changer. Our model for all cases is simple. We manufacture quantum dots. That's our core competency, and we develop intellectual property on the final products. We do have to prove out the use case, so we do need to make prototypes of final products, and we're doing that with the film, the greenhouse film right now, with a contract manufacturer in Taiwan. So we are selling direct as we prove that out. But longer term, we want to partner with like ag film manufacturers, with window manufacturers, greenhouse producers, to incorporate quantum dots into their products. And then we intend to sell those, at a good margin. But we also have the intellectual property, so we can optimize the way that we capture value by, for example, if there was a lot of markups in the value chain for Windows, we might want to just give away the quantum dots for free, because we don't want to screw up all the markups. And I'm not saying we're going to give them away for free, but we might want to, because it gets marked up 20-30% every time it changes hands. And by the time it gets to the end customer, it might be uneconomical. So we could just capture some of that value by licensing the technology to one of the final steps in the value chain, or even on that final sale, we capture 5-10%. But our intellectual property gives us that luxury. So I don't want to forget about the team. This has all been made possible by the amazing team that I've got here with me, a lot of them here in the room. We've got 12 full-time. I'm counting Dan as one of them there, including, if you add Dan, he's going to be the seventh. He's going to have his PhD soon. But we've got 6 full-time PhDs right now, not including Dan, a couple MBAs. I could just highlight a few of the people here in this picture. This is from a team building day we did up in the mountains nearby. We're in Los Alamos, New Mexico. I don't know if I mentioned that, or I guess I did, but right real close by, about 20 minutes, is the Jemez Mountains, Valle Caldera National Park. So we have skiing, rock climbing, hiking, and that gives us the opportunity to go do fun stuff like this up in the mountains. Just going from left to right, we've got Nick Archuleta there. He's one of the MBAs, actually. He works a lot on procurement and optimizing our costs and materials, and does a lot of synthesis. Damon comes from the agriculture industry. He's leading up our ag product development and pilot projects. Nikolai is our head of spectroscopy. He's doing all of the characterization and leads our thought on the materials and the physics behind them. Aaron Jackson actually comes from industry. Worked at a company called Exalta, where they were working on paints mostly for automotive, and he leads all of our polymer development work. Lizeth Guerre there is our operations manager. She is in charge of many aspects of the business, procurement, HR, a lot of things. Really lucky to have Lizeth on the team. Karthik is our director of chemistry. He leads Qualm Dot production and development. Above him there is Emily. Emily is one of our newer hires. She focuses on the window development primarily, some marketing and sales related stuff as well. Really lucky to have Emily. She came from University of Washington, Western Washington University, where we're licensing some IP. There's me. You guys know who I am. Up higher on the mountain there, or on the rock, is Chloe. She's leading the development of some of our deeper near IR materials for some interesting applications I didn't have a chance to talk about. Matt, there sitting down on the rock, was the second person to join the company. He is our chief of product and wears many hats at the business, but is essentially leading that conversation with the customer and then translating that back to the team about what is actually needed in the marketplace, what we'll sell, and what we need to do to get the product to market. And then last but not least, Andres there is working on the polymer team. He's actually the one making all of the glass laminates, so the scale-up work is largely credited to his efforts. And from my perspective, it's really a rock star team. Hits all the right points from, we've got some business expertise, we've got the technical side in all respects that's needed, coming from leading institutions. And then people that aren't shown here would be like our board of directors and our advisory board. And they bring really the heavy hitting business side. So total on our advisory board and board of directors, we've got more than $500 million of what we call exits. That means people that have built and sold companies and for a lot of money. And so they're helping guide us, in the right way. For example, one of our board members built a company up through IPO, and then he was the CEO of the company as they were publicly traded, and that company sold to Fleer, $260 million. And then we do have some cultivation experience on the team. So the bottom line with our traction is that our growth is accelerating. And here's a couple of highlights. We have exclusive licenses to intellectual property from MIT, Los Alamos, University of Washington, Western Washington University. We've raised about $2.5 million to date. We're not pre-revenue, did about $1 million in revenue last year. I've mentioned our greenhouse pilots, which is important for investors right now because that's primarily one of the things that they're most excited about is this first product and traction on that, and that's a good example of it. We'll be launching our first pilots for the window product later this year. The critical milestone for that was a large enough scale to deploy into actual buildings, and I think we're almost there. We have funding from Breakout Labs, which is funded by the Peter Thiel Foundation. Look them up. It's really cool. If you're thinking about starting a company, definitely check them out, and I can make an intro. Wells Fargo has been pretty excited about our window technology, and we were recently inducted into the IN2 Innovation Incubator. This is enabling us to work with Nrel, and they're funding Nrel and funding us to continue work on the windows. And then we also have some grants that I mentioned and some partners. So pretty excited about all of the support that we've had. And this is something that would normally be in like an investment pitch, but just hand wavy arguments around financial projections. We see huge opportunities, but initially with film, later with glass, and then as our intellectual property portfolio matures and these market opportunities are further developed, we'll be able to capture value out of the intellectual property. What's next in 2019? Well, first up, we're going to crush it in the greenhouse space. We're already doing that, but we expect a lot more coming from us in that regard in the near future. We're almost to that square meter prototype scale, and that's a huge milestone for us. A lot of window technologies have a difficult time getting to that scale for various reasons, and so it's viewed as a litmus test in the industry. If we can get to a square meter and have it still look good and perform, then we sort of made it, and it's ready for selling the product. We've been making film roll to roll for greenhouse, for the greenhouse product, but there's some additional challenges of doing it with near IR quantum dots, which I'm not going to go into, but we're working on developing the near IR film, which would be useful in scaling windows faster. We're getting closer, as I mentioned, to that critical milestone of 50 watts a square meter or 5 watts a square foot or 5% power conversion efficiency, which is also a critical milestone for a viable product. And then by the end of the year, we hope to launch the first window pilot projects. And that's one of the things that Wells Fargo offered up as part of the IN2 program is the potential to do some pilots in some of their properties. And as you can expect, Wells Fargo does have a ton of real estate all over the place. So it's an exciting prospect for us to go into an actual bank at some point. Some events that we'll be at coming up. I'll be at South by Southwest for a couple days in March, so we could meet up then if you're around. For those of you that are in Austin anyway. Qualm.forum will be in San Diego, and then Springer MRS, I think one or two of us may be there for that. For those of you that are looking for a job, feel free to reach out to me. I'll have my email on the next slide. But we're looking to hire chemical engineers, physicists, mainly for spectroscopy. Essentially we have all sorts of needs at the company, but increasingly we're needing more sales, business development type roles as well. So that may not be applicable to the technical folks, but feel free to reach out if you think you might be a fit. And then what's next this weekend? I think we're going to Taos, right? Isn't that the plan? Yeah. We're very blessed to be in this ski country here with a bunch of ski areas close by. And it's kind of tongue in cheek, but we're going to go skiing this weekend. Lucky us. So I really appreciate the opportunity to present here on this seminar. Feel free to follow us on social media. Either at UbiQD or at UbiGrow. UbiGrow is the ag related brand, so you can find that on all the social media platforms. We do sell film and some swag via ubiquity.shop. Maybe bookmarks are still up there. I think we're sold out of the bookmarks at the moment, but you might still be able to buy them because we haven't updated that on the shop. Or check out our website. My email's there. And thank you very much. I appreciate your attention, and stay in touch.
Okay, thank you so much, Hunter. That was a really interesting presentation. We'll open it up to the floor, so to speak, for questions if anyone has any. I'm not sure that Hunter can see them at the moment, so I can maybe say them out loud if anyone has any. So feel free to either turn on your microphone or just type them into the chat window if you have any questions for.
Well, if anyone here in the room has questions, you can ask. You guys already know all this stuff. Well, Andres is asking about the transition from postdoc into the business, and a lot of people are like, well, where did you learn all this? I mean, you're a PhD. How do you know about like cap tables and gross margins and that sort of stuff? And I think it's just the best way to learn is to kind of fail. Don't tell that to your investor. But really, I think it was Nietzsche that said that what it doesn't kill you makes you stronger. And I think that's true. You really have to just like go out there and try. It's not easy. It's a lot of work. It's a lot of blood, sweat, and tears. But you kind of just figure it out of necessity. Otherwise, you're going to die. And actually, the fear of death is kind of a very strong motivator. And people doubting you is a very strong motivator and telling you that it's not going to work and then they're not going to invest. But if you want to go down this road, you better be pretty stubborn. I'm sorry to put it like that, and be able to take a lot of hard hits because you're going to get told no a lot. And recently, I was just looking through my folder of presentations. I had more than 500 pitch decks in there, which is kind of suggesting I've pitched more than 500 times. It's probably about right. So maybe one in every 50 or so people that you pitch could be an actual investor. And so it's a lot of people telling you why it won't work, and you have to be pretty confident and the end of the day, they're probably right, and you're probably gonna screw it up, and you just have to learn from your mistakes and keep going. But I spent a lot of time following public stocks and listening to conference calls and trying to surround myself with smart people that I can learn from. Looks like there's a few questions in the chat window. I can read those, John.
Okay, great. I was just going to let you know if you didn't see them.
Yeah, so Justin was asking about are you able to get into what the films are made of? Is it 100% Qualm dot film? No. So there's various reasons why you couldn't make a pure quantum dot film, or why you wouldn't want to. These are typically on the order of 3 to 6% by weight quantum dots, and it's an acrylate. I can't go into the exact type of polymer, but it's not too different than like a polylural methacrylate or a polymethyl methacrylate. It's obviously not those two, which are common. But we've also been experimenting. So to be the drop-in solution, you have to go in a conventional industrial interlayer in Windows, and that's typically polyvinyl butyrol, PVB. And the challenge there is that we can't react that, we can't make that polymer with the quantum dots present because of the way it's manufactured. And we figured out we're never going to ever get into the factories where it's made for various reasons. So we have to go in at the extrusion step, and the extrusion is a bit challenging because it's a high temperature melt, and we've prototyped that. I can't go into details because it's with partners under NDA, but we can survive extrusion. We've had relatively great success, I would say, proving that we can fit into existing manufacturing process for interlayers. But yeah, 3 to 6% by weight, and typically acrylates, but we're also going into more conventional polymers, industrial polymers. So then the next question was from Jim. How big is the solar window market currently? Is there another notable company at the moment? That's a good question. There aren't, as far as I know, there is not a solar window product on the market. Maybe the closest would be Onyx Solar, but they're pretty opaque, so hazy and not very transparent. So they're useful more for like cladding and less for like actual windows. I don't know what their sales are. The company seems to be doing well. I did show a chart earlier that was estimating BIPV at about 3 billion, but the majority of that is rooftop, and I don't know the breakdown. So I would say the exact current solar window market is pretty much zero because there isn't a product out there that's both transparent and generates a meaningful amount of electricity. The other companies, if you want to look into this space, there's several that are trying to vie for being a leader, be like Next Energy Technologies in Santa Barbara, Solar Window, which is publicly traded. I believe they're based in Colorado, but I'm not. Well, they work closely with Nrel, but no comment really on those guys. Ubiquitous Energy is one that we get mixed up with a lot because of the name. They're also, all three of those are organic photovoltaics on glass. And then with the luminescent solar concentrator approach, we work with several other companies. I can't say which ones, but the ones that are out there doing this similar sort of approach would be Fizzy in the Netherlands and Glass to Power in Italy. Okay, so next question was from M. How do you find your target markets for Qualm products? That's a great question. It's a long process. Initially, it was kind of, what's the value proposition? So how much value do we bring? And then how does that compare to the cost? And the best markets would be the ones where the value that you bring is really high compared to the cost. And so there's all sorts of opportunity for margin. You could share that with your customer, or you could share that with the other participants in the value chain. But that makes it a lot easier if your value proposition is strong and your costs are well below that. But then you have all sorts of other factors like sales cycle and access to market. How can you market to these people? Can you access your customers? Is it fragmented? Is it growing? And so there's a lot of factors that go into it. There's not unfortunately a simple short answer, but good question. Wilson is asking. Wilson is telling us good luck. Thank you, Wilson. Justin, you're welcome. Matthew, seems like the grow light makers might benefit from your films, enhancing the wavelength targeting efficiency. Have you looked into those players in your greenhouse pursuit, like Fluence Bioengineering? Yeah, I mean, to some extent, we were inspired by Fluence. They were acquired by Osram, And there has been some M&A activity. There's another quantum dot company called PLT that was also acquired by Osram. So people are exploring using quantum dots in lighting, and we were as well. What we convinced ourselves of was if you want to play in lighting, you need to be on chip. And that means competing directly with existing phosphors. And there is a problem that quantum dots can solve there, but being stable and maintaining, maintaining that value proposition for a long period of time, I guess it's just stability really is the issue. On chip is really, really hard. It's 100 degrees Celsius or 100 Celsius typically, with 1 to 10 watts a square centimeter, super high fluence, blue photons. It's just really, really challenging. And so we may circle back to that, but this other product has a lot lower, let's say, reliability requirements. At least the intensity of light and the temperatures are a lot lower. So we see ourselves as more competitive with lighting, because in a greenhouse you could get similar benefits by installing additional lighting, but then you got to pay for the lights, which are on the order of about 10x more expensive than where we are. And then you also have that electricity, which is about 10 watts a square foot. So if you can basically replace supplemental lighting, our product is alone, separate from the yield improvement, paying for itself in less than a year. So we see ourselves as more competitive rather than synergistic with lighting, but we could probably play in the lighting space eventually. Okay, so then Jim says, thanks, you are welcome. Daniel says, hitting the commercial viability benchmark for LSCs is a Herculean task. I agree with that. What engineering or chemical engineering type people will you take to maintain such high efficiency at larger sizes? I'm not sure if I got the question fully correct there, but I think the reason why people are skeptical on LSCs making it, first of all, is that they're pretty far from, at least until some recent results from us, pretty far from the economical viability benchmark, which is around 50 watts a square meter. Nothing reported in the literature is really that is close to that number. So that alone is an issue. And then people, when they do their back of the envelope calculations, they assume that the thing is going to produce 50 watts all the time. And that's just not the case. It's more like 20, 25 watts if it's actually 50 when it's facing the sun, because you're getting the sun moving over the building throughout the day. So actually it's even harder than some people think, because you really have to get your performance way up there. So, but why they're skeptical with LSCs is because you have to couple light over such a long distance, and most materials will either scatter light or self-absorb light too strongly for that to be possible. But I think what we're showing with some of the data I showed here is that if you have the right kind of glass and you have the right kind of dots, you can actually make relatively large prototypes that maintain that performance. You will have decrease as you scale up, but you can mitigate that by making a really low haze film, using high quality glass, and then having the right fluorophore. So I agree it's hard, and that's one reason why we like agriculture as for the first product, is because we don't have to worry so much about guiding light and hitting those really aggressive performance targets. But we still think that we're on the path to getting there, and not too far away. But I do pity the other folks in this space that are pretty far behind. Hopefully that answers your question, Daniel. Any other questions? We've used up pretty much the full hour. So thanks again, John and Brian, for the invitation. And if people do have more questions, feel free to email me or reach out through social media or whatever. But this has been fun, and talk to you guys soon.
Thank you again, Hunter. We really appreciate you all taking the time to join us. So for those who maybe joined for the first time, this is a recurring lecture series. So we'll have another speaker in 2 weeks from now, and those details we posted. And this video will be up on YouTube in the next few days. So feel free to share it with any colleagues who may be interested. Thank
Bye.